Alright, so let f of x equal this quadratic. X is greater than or equal to -1, less than or equal to 4. Find all the numbers C that satisfy the conclusion of the mean value theorem. So we are going to use the mean value theorem because this is a quadratic function. It is continuous and differentiable everywhere. So it's going to be f prime of C equals f of B minus f of A over B minus A. So let's take the derivative of f. What's the derivative of f? That's going to be what? 2x minus 1 equal equals what? 4 minus what? 4 minus -1. F of 4 minus f of -1. F of 4. F of 4 is what? For 16 minus 4 to 13. So this is going to be 13 minus f of -1 is 1. Is it 1? Yes? Yes? Anybody? 1 and then 4 minus 5. What the? Is this right? 4 minus 5. 31. Is this gonna be okay? Is everything? It doesn't seem like. Is that 5? 4 minus 5. And this we got 2x minus 1. So that's gonna be what? 12 over 5. 2x minus 1 equals 12 over 5. Really? Any mistakes anywhere?
I think it's 3.
Huh?
I think it's 13 minus 3.
F of -1, -1. Minus f of -1, negative is +1, +1 is 3. I knew it. Equals 2. 2x equal 3. X equals 3/2. So that x is what that point where the C value, no, that satisfies you. All right. Let me go back to the other one we had done last time. And the sentence frame could have been better for what we, let's see. And I did change some of it. Let me see. The way I had it is not, I moved it around. Where'd it go? Uh-oh. Man, is everything so messed up now? Like so slow. Everything's so slow. Oh man. Look, on the last one, I don't know if you want to change if you took notes on this last one we did, where we had done this one. I don't think I had it correctly. It wasn't, it wasn't exactly right. So, let G be a differentiable function. Is there a number C in the closed interval -5, -3, such that G prime of C equals -4? Justify your answer. So you're supposed to say the mean value theorem applies because the function is differentiable, and then this I didn't have, and therefore continuous. on the closed interval. This is more specific to what it is. So I don't know if you. This is better than what I had. What I had was something like the mean value theorem applies because the function is differentiable on including -5, -3, but it's not. It should have this continuous part, and therefore continuous on the closed interval -5, -3. So this is a good sentence frame. What I had before was right, exactly. All right. So let's go back to doing this lesson then here. Okay, so this is a long lesson, everybody. So 5.2 extreme value theorem. Absolute maximum and absolute minimum values of a function. If a function f is continuous, okay, absolute maximum and absolute minimum values of graphs. If a function f is continuous, I hope it. If a function f is continuous over the interval including a, including b, from a to b, then f has at least one maximum value and at least one minimum value on including a to b. So you got this continuous function f here, and if it is defined at the endpoints, it has to be defined at the endpoints. It can't be open, it has to be closed. If it's closed at the endpoints, then it must have a max or and a min. So for this particular one, you could see that the minimum of this function would be right here. That's the lowest. That's the minimum. So the absolute maximum value of f would be here. So I got this. The absolute maximum value of f is, and it occurs at. So you see that this would be the max, absolute max, the highest, and this would be the absolute minimum right here, the lowest. So the absolute maximum value of f is whatever that number is right here. Whatever this is the absolute maximum right here. Whatever the y value here is. And it would occur at this x value here. And the absolute minimum would be at this x value here. And the absolute minimum would be whatever the y value here is. So let's just say it's c f of c at x equal to c. I'll use the absolute minimum value of f is d. Let's say this is d, whatever that number here is. The absolute minimum value of f is f of d, and it occurs at x equal to d, whatever that is. Number. Okay, so here's a particular situation here. What if it's horizontal? What if the function is horizontal and it is closed at the endpoints? Does it have a max or a min? Does it have a max or a min? What do you guys think if it's horizontal? Does it have a max or a min? So what happens here is that each one of the points in there, each one of those points is a max and it's a min. They're all maxes and mins. So all outputs of f on the interval AB are maxes, maximums, and minimums of f. I had it open again. I'll try to have these lessons open the day before, so you just go and copy down the notes, and then we can just discuss, talk about it, so we can go a little faster. I'm going to continue on. Okay, so what are relative local minimums and what are relative local maximum values? So there are those absolute max and absolute mins, and then there are those that are relative max, relative min, meaning that they are relatively minimum, relatively max. They're not the absolute max. Let's see. What does it say? The relative local maximum of value of f is, and it occurs at, okay? So in this particular function, the absolute maximum value would be, this is the absolute max, no? Right here, this is the absolute maximum, the highest. That's the highest. So this is a relative max because it's not the highest, but it's higher within its like close to its neighborhood here or right here. And where in this situation, this was the absolute minimum, but this is relatively min compared to its neighbor, everything here. So the relative local maximum value occurs, value of f is relative max would be here. So this is a relative max. This is the relative max. It occurs at E, let's say f of E. And a relative min, this one would be a relative min. This one is a relative min because it's not the absolute min. That's the absolute min. This is a relative minimum. So a relative minimum value of f is f of g, x equal to g. So that's graphically, that's what it is, talking about absolute maximums, absolute minimums, relative maximums, relative minimums. Okay, so now let's do some problems. I'm going to continue now. You can go back and if you miss anything. Problem 1. So let f of x be this fourth degree polynomial. From x is greater or equal to -1, less than or equal to 4. And there's the graph. Yeah, I guess I'm giving you the graph for it already. Let me give you 3-4 minutes to copy this down. Go ahead and copy it down. You could go ahead and save the function. Put it in the calculator. Put it in your calculator, and then just evaluate what would be the absolute maximum. The absolute maximum looks to be here on the left side here. Yes, no, right there, no? Yes. So what we could do, it looks to be something like 35 or 37 or something like that. Let's practice using our calculators as well. Copy it down. Get your calculators, input the calculator, and then just go ahead and do f of -1. What is the absolute maximum here? So let f of x so input it. So f of x control enter f of x equal 3x to the fourth, 3x to the fourth minus 16 x to the third plus 18x squared. Enter it. So it saved it. And now go ahead and do f of -1. Since we do have the graph there, f of -1, just do what is f of -1. Evaluate f of -1. F of -1. Enter it. Yep. So you guys did putting it into the calculator? Getting it? What did you guys get? What is it? What's that for -1? 37. It is 37? Is it? So the absolute maximum value of f is 37, and it occurs at x equal what? X equal -1. So what is the absolute minimum? What is the absolute minimum? Where does it look to be the absolute minimum at? X equal to what? X equal to 3. Let's go ahead and just do f of -3. What is f of -3? What's f of -3? What's f of -3? Um, what did I see? Negative 3? It's f of 3. No? F of 3. I put f of negative 3. F of 3, not f of negative 3. F of 3. What's f of 3? Negative 27. So it occurs at x equals 3. That's the minimum right there on that interval. What is the local maximum? What is the local maximum? Where does it occur? X equal to 1. X equal to 1. So what are we going to do? F of 1. What is f of 1? What's f of 1? 5. So the relative maximum value of f is 5, and it occurs at x equal to 1. And then what is the local minimum? Where is the local minimum? At x equal to what? Where? Where's the local minimum? So it occurs where? At x equal to 0. So the relative minimum value of f is 0 and occurs at x equal to 0. All right, moving on. Next. If it's not closed, which this is not closed, this function will have no maximum or minimum on its interval because it's not defined at its endpoints. So, like I just said, in the other ones, it had to be defined. It was closed. This, if it's not closed, then it will not have a max or min. So not all functions attain a maximum or a minimum value on the interval. So this rational function here will also not attain a max or a min because it goes on forever. So it goes up forever. So it has a infinite. It's infinite going up and infinite going down, so it has no maximum or minimum. This function has no maximum or minimum on the interval from -4 to 0 because it has a vertical asymptote within the interval. Alright, moving on. You can go back and copy. this. Problem 2, use the graph to answer the following questions. What is the absolute maximum of this function? What is the absolute maximum of this function? What do you guys think is the absolute maximum? Huh? 4? Anybody? Is it 4? Would it be 4? Why would it not be 4? The endpoint on the left is not defined, so we wouldn't have a max. If we follow what we just what it says, what we just came up on the definition, the function does not have an absolute maximum value because it's not defined on the left end. What is the absolute minimum? So maybe what was it? It's confusing that that particular one I had given you was open and like this. So when it's something like that, it definitely has no absolute max or no absolute min. But if it was like this, bubbled in and not bubbled in, so it wouldn't have a max, an absolute max, but it does have an absolute min, no? Because it's defined. Yeah? That makes sense or no? And it would have a relative. Okay, so let's just kind of look at what we have there. So what is the absolute minimum? Does it have an absolute minimum? What do you guys think it is? What is it? What's the absolute minimum? Is it 1? The absolute minimum value of f is 1, and it occurs at x equal to 4. What is the local maximum? Does it have a local maximum? Four and what else? 4 and 3. Because locally, what it's saying is around this neighborhood and around this neighborhood, this is the highest, and around here is the highest. So they have to be local maximums. So the relative, local means relative. The relative maximum values of f are 4 and 3. And they occur at x equal to 3 and x equal to 6. What is the local minimum value? What's the local minimum value, anybody? Huh? Local minimum. Local minimum. Would this be a local minimum right here? Huh? Is it a local minimum? Relative to like around itself, is it lower than any of these points? Is it? So it has to be a local minimum. So this is a local minimum right here. This point here is the absolute minimum. Is it a local minimum? It's also a local minimum. So around its neighborhood, it is lower than its local than the points here, or these are ones. So locally, it's a local minimum and it's an absolute minimum. So we would say that local minimum would be 2 and 1. So the relative minimum values of f are 2 and 1, and they occur at x equal to 2 and x equal to 4. All right, so maybe you I don't know if you would have a question on what this is. Is this anything here? This one right here, is it anything? So some books have it that this is a local minimum because it's lower than the points here. But in some books have it as not being a local minimum. If it's at the endpoints, try not to even worry about it unless it is a absolute minimum. So if it was like right here, instead of there, then it would be an absolute minimum. But otherwise, don't even say it's anything at all. So unless it is an absolute minimum at the endpoints, don't even treat it as anything local. So that wouldn't be. All right, moving on. (5.2) Critical numbers of a function. A critical number of a function f is a number c in the domain of f such that f prime of c is equal to 0 or f prime of c does not exist. In this particular graph, f prime of c is equal to 0 is where the slope of f is equal to 0. So here, this is f, so the slope here is 0. So this is a critical point right here. So whatever this is, that's a critical point because the slope is 0 there. And then where it doesn't exist would be this one here. So this is also here a critical point because its tangent here is does not exist, is straight up and down. So that's a critical point, and that is a critical point right there. Yeah.
Can you go back to the last one?
To the other one?
Yeah. Oh, that's just-
So the function f has a critical number at c equal to 0 because it has a vertical tangent line at that point, and f prime of c does not exist. So whenever it has a vertical tangent line, it does not exist. All right. So now we are going to find the critical points or the critical numbers of this function here. Here we go. We're going to find the critical numbers of this. What are we going to do? Is this the product rule? Yes or no? Product rule. All right, let's go. Let's do it. F prime of x is going to equal to the first times the derivative of the second, and the derivative of the second is what? Negative 1. Negative 1. First times the first times the second. How does it go? The first times the second. Is it minus? Is minus? Or is it plus? Plus. First times the second plus the second times the first. Okay. First times the second plus the second times the derivative of the first. 3/5, and then what? Minus 5 over 5, which is going to be negative 2/5, which is going to be x to the 2/5 at the bottom. What are we going to do now? And we're going to set it equal to 0. All right, so this thing is going to be negative x to the 3/5. Are we going to distribute this? I don't know. Let's distribute. And we're going to set it equal to 0. So if I do distribute that, that's going to give me what? 12 plus 12 over 5x to the 2/5. I don't know. Let's see. And then this is going to be minus 3/5. And you got x, and then we got x to the 2/5 equal to 0. Yeah. What we could do is have a common denominator. See, this one's already that, and then that, and then this one. I'm going to put a common denominator. So this one, let's just do it like this. 5x 2/5, and this times it by, which do at the bottom, do at the top. 5. All right, so we have a common denominator. Common denominator. So put it under one of them. So that's going to be negative 5. When you multiply, you add this. It's going to be 5 over. Oh, is that going to be x? 2 plus 3 is 5 over 5 is just going to be x. Yep. Plus 12. Minus 3x. Can we just cross multiply this thing? So this times that is that. This times this is 0. So we're gonna have negative 5x plus 12 minus 3x is equal to 0. And so what we're gonna have here, so it's gonna be what? Negative 8x plus 12 equal to 0. And so what is this? Minus 12? Minus 12 equals negative 8x divided by negative 8. So we're going to get x equals what? Divided by 4, it'll be 3 halves? Yes? So now, I have done something that you have to always go back and really look out for this. So definitely we got this answer, no? This is a critical number, 3 halves. There will always be a problem here at the bottom. X cannot equal to what? X cannot equal to what? 0. If I plug in x as 0 here, 0, that'll be something divided by 0, which we cannot do. So x equal to 0 is also a critical number. So these are the two critical numbers. And that's the graph we just did do before. At x equal to 0 and at 3 halves. And that's the graph of f right there. All right, let's go to 4a. Now let's do something easier. This is what you're gonna do, like easier. Find out the critical numbers of this. So what's the procedure for finding critical numbers? Take the derivative, set it equal to 0. So f prime of x, that's going to cancel out, x to the third, that's going to cancel out, it's going to be minus x squared, minus 2x equal to 0. What do we do here to factor this out? It's a cubic, they all have an x, take out an x. This will be x squared minus x minus 2 equal to 0. So x equal to 0 is already a critical number, x equal to 0. And then this one can be factored out to be what? This is going to be what? X and x. What are the numbers here? What are the numbers? So x equal to what? 2 and x equal to 1? Negative 1? So here, 0, 2, and negative 1 are the critical numbers. All right, B, let's go to B. We're almost done here. So we're going to take the derivative of this. So this is going to be f prime of x is going to equal to. Is this a chain rule? Yeah? A chain rule, no? You guys want to look at the little machine? You guys want to do it with the little machine thing? Which one is the outer and inner? Is in what? Which one is the inner? This is, would this be ln x? Is that ln, then this is... Man, I'm really confused with doing it like this. It would just be the, how does it go? What's the derivative of this? So be on top, 2x plus 1, yes, and leave it there at the top. And then ln, what's the derivative of ln x? What's the derivative of ln x? 1 over x, where x is what? X is this quantity, no? So it would be x squared plus x plus 1. Can we factor this out some more? Instead of equal to 0, we're going to set it equal to 0. We took the derivative of it. So this f prime of x. At the bottom, it will never be. Alright, let's factor. Can we factor out the bottom? What would be the bottom? Bottom would be. Can we factor out the bottom? Can we factor this? What would it be? Is it? No, we can't factor this out, can we? What is it? Can we factor out the bottom? So this one it will never be 0. The bottom will never be 0, so we got no problems with the bottom being 0. If we were to graph it, it would probably be somewhere on top like this, that the function will never be 0. I think if we graph it, no? So we will have no problems with having a vertical asymptote. So the problem is only at the top. So we cross multiply here. So it'll be 2x equal to 2x plus 1 equal to 0. So x equals what? Negative 1/2 is the only critical number. All right, we're done here. So that is it.